Okay, so we already went over the warm-up, but just as a quick recap, this is a telescoping series. You have to factor it, then you have to find the partial fractions, and then always write out the terms at least until you can see that everything beyond the leading term or terms is going to cancel, right? And then once you've got that, then you get your sum. Technically, you should say 1/6 minus the limit as n approaches infinity of this guy, which is going to be 0. So it's 1/6. Okay, today is our second day of Taylor polynomials. 9-7 part B. At the end of this lesson, you will be able to determine and apply the remainder of a Taylor polynomial. Are we ready?
Yeah.
Okay? Good. All right. This part you don't have to write. It's just to talk about for a minute. So there are, as you know, a Taylor polynomial is a polynomial that approximates a non-polynomial function, right? So those functions that are not the traditional functions, which are the rational, radical, polynomial, those kinds of functions, all of those, the other functions are called transcendental functions. And so what we're doing is we're using polynomials to approximate the transcendental functions, the exponentials, logarithms, and trig, basically. So just a little comparison. When you used to do linear approximation, all you did was find the equation of a tangent line, and then you plugged a value that was near the point of tangency into the tangent line instead of the function, and used that to approximate the function value, right? Here, we have a Taylor polynomial approximation. So say we have some Taylor polynomial that's centered at some certain value, and we want to approximate the value, the actual function value, at a point near there. Instead of plugging into the actual function, we can plug into the Taylor polynomial and find an approximation for the actual value. So when you're doing a Taylor polynomial approximation, all you do is find the Taylor polynomial and plug the number in there instead of the actual function. All right, it's very similar to linear approximation. Okay, so we're going to start simple. So we're going to use a fourth Maclaurin polynomial to approximate the value of e to the 0.2. So the first thing you're going to have to do is find a Maclaurin polynomial approximation for e to the x. And of course, where would we want the center to be? If we want to plug the 0.2 in, where do you think would be a good center that's near 0.2? 0, right? Pick an integer near there, right? Centered. Oh, and it's Maclaurin. Yeah, I know. I keep saying centered at 0, but it's funny because I think every single problem in your homework tonight is Maclaurin. So I think they're all centered at 0 tonight, if I remember correctly. So I'm still going to ask you for the center anyway, just to reinforce. But yeah, so we're going to center at 0. So take a minute or two. You might still have this in your notes from yesterday, but if not, just take a minute and figure out the polynomial approximation for e to the x. Centered at 0.
Wait, are we doing e to the x or e to the 0.2?
Well, you have to have a function and then you're going to plug the 0.2 in.
Oh,
right?
How do we know what number or like, no, okay.
What's up there?
Oh, wait, it's the fourth. N is 4. It says
sorry, my bad.
Yeah, I'm sorry, it's written in words, not numbers, so that might have thrown you off. Yeah, guys, your N is 4. It's the fourth Maclaurin.
Do it.
I know everything like a weird center, it'll give you
So use a calculator.
Okay, we're centered at 0. Do you need a calculator? What? No. Oh, to plug in the point 2.
Yeah.
Yes, I'm sorry, just to find the polynomial, I'm sorry, I thought we were all just to find the polynomial. You don't need a calculator for finding the polynomial, but yes, you will absolutely need a calculator today to plug in all these decimals, because it's all going to be decimals today.
Why are we just finding the value then? Don't answer that, it'll make me mad.
Because there's all kinds of wonderful applications for using approximations of functions, right? Rather than actually using the functions. We know that they're used in engineering.
It's just kind of making me mad. Like, I'm wasting my time. Sorry, that's not
Okay.
It looks like you're just as frustrated as us.
No, I see tremendous value in this.
Oh, yeah?
I do. No, I don't know enough to know, so I can't speak to it. But I can tell you that, based on Mr. Thomas's former student, there's lots of engineering applications for this, right?
See.
Okay.
I did it.
I'm curious if any of you guys end up becoming engineers, which chances are pretty good that quite a few of you will. Come back someday and tell me, right? I'm very curious to find out if you do use approximations. Yes?
I asked my dad, and he said electrical engineering uses the negative, or the I, imaginary numbers.
Oh, really? Oh, that's good to know. Okay.
My dad's a chemical engineer.
He uses Euler's method? Okay. Okay. Huh. So, do you guys hear that? Yes. So, Annika's dad is a chemical engineer, and he uses Euler's method. Hey. Actually, there's like a computer program where you plug in the variables that you need to, but the computer uses Euler's method to find those approximations. That's good. I like that. And I need another minute? All right. Check your answer.
So, once we get, it's like once we get our equation, we just plug it in.
Just plug it in, right? So far, so good, right? Here. Need help? You got it? Good, okay, we're on our way. Are there any questions on this? Did everyone find the correct polynomial? Yeah. Right? Okay, it's good to know, it will come in handy today to just kind of know that the Taylor polynomial for e to the x is x to the n over n factorial, right? If you kind of, have that in your pocket, it makes things go faster a little bit, right? So, anyway, so there you go. So there's your e to the x polynomial, 4th degree Maclaurin, and then you plug in your point 2 and you get your answer. Okay. Pass the screen? Okay. So, we have that approximation, but, how good is it? Well, let's see. There's a couple ways to improve the accuracy of an approximation. One would be to move the x value closer to the c value, or vice versa, and then another, of course, would be to use a higher degree polynomial. But how do we know if we need more degrees, a higher degree in our polynomial? How do we know if we need improving? How do we know how close we are to the actual answer, right? Okay. So, if you think of the actual value as the approximate value plus a remainder, right? So say we were actually finding e to the point 2. The actual value of e to the point 2 equals the approximation we just found plus some stuff that's left over. So we call the stuff that's left over the remainder. The error is the absolute value of the remainder, which means the error is the absolute value of the true function value minus our polynomial approximation. Taylor, who came up with the concept of Taylor polynomials, also came up with a theorem on how to calculate the error in a polynomial approximation. So, he said, if f is differentiable through order n plus 1 in an interval containing c, then for each x in the interval there exists some z between x and c, such that the remainder is the n plus 1's derivative of f at z divided by n plus 1 factorial times x minus c to the n plus 1. Alright? Now, we are going to use this formula, but we're going to use a modified version of it. Now, you can say thank God, but don't thank him yet because it's not easier. So here we go. Okay, so here's the thing about this formula that makes it tough, is when I first started learning it, I know what x is, I know what c is, I know what n is, I don't know what z is, right? So I started looking and saying, well, how do you find z? Z is some value between x and c, right? We don't know what z is. And after reading, not just in your text, but like all of the different people that publish notes online and everything, it is nearly impossible to find z. So, rather than trying to find z, instead we do something else. We use this formula. And I'll bring it up a little bit. So, here's what this says. If this is the exact remainder, then the actual remainder has to be at the very, very most, so less than or equal to, if we took this same part of the formula, so the x minus c to the n plus 1 and the n plus 1 factorial haven't changed, this is the only thing that we don't quite know. So rather than trying to figure it out, we just take the maximum possible value for that derivative on the interval from x to c or c to x, depending on which one's lower, which one's higher. This kind of reminded me a little bit of the error formula that we used when we did trapezoids and Simpsons, right? Yeah, it's a little bit like that. So this is the formula we're going to use. So our error, rather than finding the exact value of the error, we're going to find a maximum value for the error. Does that make sense? Okay. All right. Okay, I'm going to walk you through an example slowly and carefully, okay? So the third Maclaurin polynomial for f of x equals sine x is given by this. All right, this is our third Maclaurin polynomial. We're going to approximate the sine of 0.1, and then we're going to use Taylor's theorem to determine the accuracy of our approximation. Sine of 0.1, if we approximate it, it's just plugging a 0.1 into our polynomial, right? So our approximation is just p of 0.1, and you end up with 0.09983333. Everyone okay so far? Okay. All right. Now we go to our error formula to determine how accurate this answer is. So the error formula says that the absolute value of the remainder, which is the error basically, has to be less than or equal to this formula. For this problem, our x, that's our input value. That's where we're finding the approximation. Right? So think of this as like a p of x, so our x is 0.1. Our c is 0. This is a Maclaurin polynomial. So our c is 0. This is a third Maclaurin polynomial, so our n is 3, which means our n plus 1 would be 4. So we'd have a 4, we'd have a 4, we'd have a 4. All right, so far all I'm doing is walking you through how to plug stuff into your formula. Any questions on what x is, what c is, or what n is? Okay, then we plug in. So we get 0.1 minus 0 to the fourth over 4 factorial times the max value of sine z. And this max value of sine z is on the interval from c to x, so on the interval 0 to 0.1. There's a lie on the screen. I saw some furrowed brows. That's good. So 0.1 to the fourth, 0.0001, 4 factorial is 24. So this is the max of sine z on 0 to 0.1 is 1. Is that true? You can say answer the question. No, it's the max of sine on all x, right, for all x, but it's not the max of sine on the interval from 0 to 0.1. I will tell you, this was the part of the chapter that gave me the hardest time. And everything that I looked up, everybody that does these problems where they involve sine or cosine just automatically uses a max of 1, regardless of interval. I don't know why, but they do. That is the accepted norm. The book does it. The notes that I usually go to online do it. Everybody's doing it, right? So we do know that it's a true statement. The remainder will be less than that, right? Because that's higher than the actual max. So just know when you have a sine or a cosine that the max value they're going to use is 1. Because it's true then for all x. I know, it doesn't sit well with me either. Personally, I would plug the 0.1 in and get that actual max value, because you know that your error is going to be even less than this. But I gotta tell you, even with a 1, it's a pretty good error, right? It's not bad. Okay, so we blah, 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 blah. Oh, here's my little explanation. So we know the max value of sine z between 0 and 0.1 is less than 1. So we're plugging in a 1 for the max, means that the remainder has to be less than that value. So our remainder has to be less than 0.00004167. For some of the problems, they want you to write the interval that the actual value has to be between, right? So the way you do that is if you take your approximation, this is the maximum error, which means, and we don't know if it's like if this is bigger than that or less than that, right? So all we know is if we take our approximation and then subtract that and add that, that the true value has to be in between there somewhere. So to find the way that this answer is written is you just take your approximation and then subtract and add the error to it to get the true, and then the true value has to be in between. How's that sitting? Nikhil, how you doing? Yeah, Bethany.
So if you didn't have a sine or a cosine, how would you know what to plug in?
You'd have to find the fourth derivative of the function, and then, yeah, or third, is it third or fourth? No, it was fourth for this one, right? So you'd have to find the fourth derivative, and then hope that it's always increasing or always decreasing, and then plug in the endpoints and see which one's the biggest, right? Yeah. I will tell you, for all the homework problems that I looked at, the problems were all functions that were either sine, cosine, e to the x, or e to some exponent, or ln x. So sine and cosine, you can just use 1. E to the x and ln x are always either increasing or decreasing, so you could just plug in the endpoints. Right? So it was not heavily emphasized in the problems, that max value. All right, let's try another one. I mean, no. That was our first, that was just our example. We haven't even done any where you guys did it. Here we go. All right, so I want you to find an upper bound for the error. Upper bound just means the max error, right? Okay, so Find an upper bound for the error of the approximation for E if E is roughly equal to this. Now we all know our polynomial approximation for e to the x is x to the n over n factorial. This is an approximation for e to the first, right? So that should kind of help you figure out what's x and what's c. So first thing you want to do is figure out what's x and what's c. This messed with a lot of people during first, and it was not to say that people were bad, it was my terrible presentation. So I'm trying to clarify this. So one of the things that I did was just wrote out, again, that Taylor polynomial for e to the x, just so you can kind of see, all right, we're plugging in a 1 for all the x's, right? So our x is 1. The way you know c is whenever you're doing a Taylor polynomial approximation, the x that's raised to the power, if there was a c, it'd be x minus c, right? Say c was 2, you'd have x minus 2's all the way along, right? So if there's no x minus something in parentheses, c is 0. Does that make sense? Okay. All right, I want you guys to try it. So we have, you can figure out n by looking at the terms, right? So you've got your x, you've got your c, you've got your n.
What's our C? Oh, 0.
Yep. Find that remainder. Come into the back.
Since the maximum value of e to the x between 0 and 1.
It's gonna be very long.
I have it written because sometimes c is less than 1, so it's either use those two numbers.
What? That's what I did. What is the max error? So it lies between that and that.
No.
Oh, yeah. That's okay. What is 6?
I go back and
So it's the 6. So then it's just the 6 here will
And then look at what
max is that. So it's
I have
yes, we're trying to find an approximation. We're actually trying to zero out after your head. We're trying to
so 0.
and then your
Where's the baby book?
I know.
I think I have. But I didn't. Remember you came back to the I don't know. I'm not looking at
Yeah, I know it's right. Yeah. So you need
Oh, I think it's just. Yep.
All right, let's take a look and see how you did. Okay, so we all got x was 0, c was 1, and then to figure out n was 5. Yes? Okay, good. Now, remember, if your n is 5, you use n plus 1 all through the formula, so you're actually using 6, right? All the way through. All right. So, when we plug in, we get that our 5th degree remainder, our r sub 5 of 1, is 1 minus 0 to the 6th over 6 factorial times the maximum value of the 6th derivative of e to the x on the interval from 0 to 1. You're always checking, your interval where you want that max is always between x and c. Whichever one's lower, whichever one's bigger. But it's always between those two numbers, right? Z always falls between your x and your c. So, you find the max, what's the 6th derivative of e to the x?
E to the x.
E to the x, right? So really we want the maximum value of e to the x between 0 and 1. E to the x is always increasing, so you just have to check the endpoints. What's e to the 0? What's e to the first? Which one's the biggest? That's your max value. Okay? Alright, so we get e, because this is just 1, right? E over 6 factorial 720, and that's our error approximation. How'd you do? That okay? Yes.
So on the test, we have to write out the test.
On the test, it's going to actually word it a little differently. We'll get to those types in just a second. Yeah. All right. Now, this problem had a second part, right? This was kind of like part A, and then this was part B. Part B said calculate the exact error. So, to calculate the exact error is just the difference between the actual value and the approximation. So the exact error would be what E is minus what this is. Does that make sense? Okay. So, for example, suppose E is around 2.71828182, right? Okay, so we get our value for E. This right here, that's our approximation, whatever that may be. So if this is the real value and this is the approximate value and we subtract, right, the answer that we get would be the actual error. Here, let's find it. Okay, so if you were to actually do that Taylor polynomial approximation, this one right here, you actually get, what was it, 163 over 60? Is that what I was saying? Yeah. This value is 163 over 60. So this approximation. So 163. Okay, someone tell me what 163 over 60 is as a decimal.
2.7166.
Right? So if you subtract those two, the answer is the actual error. Right? True value minus approximation equals error.
Ms. Price?
Yes.
So does it not actually have like anything to do with the other part of the problem?
The other part of the problem is telling you what the maximum possible error is.
So they're not like
This is called the upper bound of the error. It's the highest value you could have of error. This is what the actual error was. And I think they're having you do this in your homework tonight just to kind of check and see, oh yeah, it really is less than what we predicted as the upper bound of the error. It worked.
So,
Okay. Yes, Stephen?
the formula gives us the maximum number the error could be.
Yes.
How do we find what the error actually is then?
Okay, so the exact error is the actual value of E, right? You just, in your calculator, do E,
What if
right?
you don't know what E, like what if I'm not given such a nice number as E?
Whatever it is. Say it's like sine of 0.2. On your calculator, you just literally do sine 0.2, enter.
Oh, okay.
Right? Okay, so E minus your approximation. So this is the exact minus the approximate equals actual error. Yes, sir.
How'd you get 163 over 60?
just added, literally added this together. Like this was our approximation. Yes.
How did you get
Okay.
2.7? No, 2.1.
162 divided by 60 is 200.
Where did you get 164?
Oh, because if you add the
I will.
1 plus 1.
You have to add all that?
Yeah. It's not that bad.
Yeah.
Deep breath, here we go. Okay. All right. Next. Okay, so now we get to kind of do it backwards. Right? I know. So now what we're going to do is we're going to figure out the degree. The degree is the same thing as n, right? So we're going to figure out what n value of a Maclaurin polynomial is required for the error to be less than 0.0001 if f of x is e to the negative x and we are approximating f of 1. Now, let's figure out the first few things that we know. We know what our x is. What's x? 1. What's c? 0. How do you know it's 0? It's Maclaurin. How did you know x was 1? Because it says we're approximating f of 1, right? So, we know x is 1. We know c is 0. Do we know n? No, that's what we're trying to find, right? That's the whole question, is what's n. Okay? So you're going to plug everything in except the n's. N stays n. Now, we have to figure out the maximum value of the nth derivative of e to the negative x on the interval from 0 to 1. If you do the nth derivative of e to the negative x, you're going to get negative e to the negative x, positive e to the negative x, negative e to the negative x, positive e to the negative x, right? But if you look carefully when you're doing these, it's the maximum of the absolute value, so that coefficient, that negative in front, is irrelevant. You see what I'm saying? You just go with the absolute value. All right, so everyone see if you can figure it out. With no help, I want to see if you can do this. Start to finish.
I know what I do.
Well, start by plugging into your remainder formula. Plug in x,
Oh, yeah.
plug in c, and see if you can figure out that max value. The max value is the part that is a little tricky. It's not that. Max value of e to the negative x on 0 to 1. That is e to the negative 1. Remember, you're finding the max on 0 to 1.
But e to the 1.
Yes.
But it's still like
We always use this. Always use this. That's your remainder. It would be like the remainder of that nth polynomial approximation. It's also called the small remainder.
okay, so also what is like the like
Less than the error. Oh, so n is higher than degree of the polynomial. What is the error? Right? So it's like higher than right? Here we don't know what it's but it's how it's the degree of the polynomial. Or your x is the value where your x plugging into the polynomial, and c is where the polynomial is set.
so are we just trying to can you tell like what is like
For this one, we want to know.
that's your remainder, but then what's like this are you finding your
Are you talking about a specific problem or just a problem? And I was like, what? Well, the total polynomial itself is just a polynomial that mimics the actual. So anytime you plug something into the polynomial
pretty close to the actual function value. It won't be exactly the same, but it should be close. And what we're trying to find in this problem is how far do we have to go out for our Taylor polynomial approximation to be 0.0001.
I got this number.
Oh, I got
Okay, here's like, dude, what are you doing? Here's what here's
Why
what
do we want to change the function to polynomial?
Then you type it.
It's just because polynomials are different. So when you're doing work with the functions, you don't have access to the source exactly. But you work with the polynomial approximation.
Oh, hell no.
I'm just gonna like go on.
Oh, yeah.
I like watching videos.
40 seconds, 5 seconds,
Yeah.
Yeah.
Oh, this is really lost.
Yeah.
Oh,
That's why I'm
Oh,
asking you.
you're way behind, yes. Oh, that makes sense. Okay, hold on. Okay, watch the video.
Yeah.
Because it really will clear it up.
Yeah, because I watched the beginning of it.
Okay. Polynomials are easier to understand. They just are very easy. You can always differentiate the polynomials and gradients faster. Right? So this mathematician Taylor, and this was another. Anyway, he said, no one is and so that's why it's called Taylor polynomial. In order to do
Oh, yeah, I
it,
know.
starting point in the polynomial. No, she like looks as starting point C. That's what
I
it
hate
says.
that. Like he's right in front
Right?
of me.
So and you like
at least you try to hide it.
all of the functions.
Sometimes I'm just like this.
It's like this. But it doesn't have to be zero. You can center it anywhere and then you can follow it when it branches out. Yeah, and then you have to solve. And I just did it with yes and check.
You get, and it's what do you
I have an idea.
I got it. I got it.
Why would it
I got it.
I was like,
Besides showing them enemies.
Okay, so you have n factorial. Okay, is less than or equal to? Yeah, because it can't just, you're gonna get, right, because the factorial has to be integer.
Yeah, but your Y's on your
I'm not sure, but can't.
I see that, yeah.
Oh, okay, well.
Oh, so I just think that all is
You might want to resend your calculator, bro.
So you can, 1 divided by 0.00. Oh, and then I just guess and check. Yeah. Oh, yeah. Because you know it's not gonna be some super crazy number. So, yeah, so let's just walk through this real quick. Okay, so x is 1, c is 0. So you end up with 1 minus 0 to the n plus 1 divided by n plus 1 factorial times the max of the n plus 1th derivative of e to the negative x on 0 to 1. So the n plus 1th derivative of e to the negative x is e to the negative x, right? Regardless of the negative because it's absolute value. So you plug in a 0, e to the 0 is 1. You plug in a 1, e to the negative first is 1 over e. What's the biggest of those two? 1. So our max is 1. So we just have 1 times 1 over n plus 1 factorial is essentially what we've got. So blah, blah, blah. Says max is 1. So essentially we end up with 1 over n plus 1 factorial is less than 0.0001, right? This is always positive. This is positive. So you can go ahead and cross multiply without any problem. So when you cross multiply, you end up with n plus 1 factorial being greater than 10,000. And then I just did it by guess and check, right? You could sit there in your calculator, put n plus 1 factorial or x plus 1 factorial into your y equals and just look and see once you hit a value that's bigger than 10,000, right? But I just did it with guess and check. So 8 factorial is greater than 10,000, which means our n has to be 7.
Where's your solving?
Yes, Stephen.
I got the same answer with the numbers that I had.
Yeah, where did, oh, okay, because consonant.
The numbers, which numbers?
So like the thing that I ended up plugging into my table was n plus 1 factorial, and then I found out when that was bigger than e over 0.0001.
So you got your max derivative value as e?
Yeah.
Were you plugging into e to the negative x?
Oh, that's probably my mistake.
Right. It probably didn't affect it enough to make it a big enough difference, because e is just around 3, and this is just the difference between 3 or 1, like 30, let's see, 30,000 versus 10,000, it probably was the same factorial, so it didn't be, okay. Yes?
I'm confused how you got from the formula to like 1 over n plus 1 factorial. Is less than.
Oh, okay. Well, 1 minus 0 to the n plus 1 is always 1,
Oh.
right? Because 1 to any power is 1.
I had to think about it.
Right? Yeah. And then this max we figured out was 1.
Yeah, I got that.
Okay. Yeah.
Okay, yeah.
Yes.
So it's the first number that's greater than 1.
The first number that works. Yes. Yep. Good.
Okay, so if it was like 2.
All right. Hey, is there time for one more? Oh, yes, there is. As a matter of fact, not just one. We've got 2 more. Here we go. Okay. So, sines and cosines. I did a sine example earlier, and I lied. Okay? So, I did. So, here's why. I didn't really lie, but I misled, and I'm going to kind of lead you in a new direction now. So, sines and cosines, every other term is 0 with the polynomial. Did you guys realize that when we were doing them last night, right? Because the sign is 0, 0, so every other term always drops out. Okay, so what happens is with sine and cosines, the tradition, it's another one of those traditional things with sine and cosine. Not only do we always use a max of 1, but the tradition is if you're given an approximation for sine x like this, you assume it's a 4th degree, not a 3rd degree. You always add the invisible 0 that's beyond. Okay? I know. Because every other term is 0, right? So you just, whenever you're given a Taylor polynomial approximation for sine or cosine, you always assume that the next term is there and just went to 0 and is not written. So, we want to determine all values of x. So this is the last type of problem you're going to see. Now, you know the error, you know c, you know n, you don't know x. So now we're going to find all the different values of sine that we can plug in. How far out can we go from the center and still have an error that's less than 0.0001 or 001? All right? So now we know c, we know n, we don't know x. So, here's me writing out about how it ends in an x cubed. We normally let n be 3, but because this is sine, we're going to let n be 4. I couldn't tell if that was shock or yawn.
I was yawning.
Okay, good. All right. Okay, so if n is 4, so we're going to find our remainder based on a 4th degree. So we plug in, we get x to the 5th over 5 factorial times the maximum value of cosine between 0 and some random x. By the way, it was the 5th, I didn't walk you through, but this is the 5th derivative of sine. So if you need me to walk you through, I can, but that's the 5th derivative of sine. Okay. The nice thing about sines and cosines, it doesn't really matter which derivative it is because the max value is always going to be 1. All right, so we want this to be less than 0.001. I think I'm going to cover this up and make you guys figure it out. Take a minute, see if you can figure out x. Remember that max for any sine or cosine, it's always going to be 1. will be a decimal. Yes, I don't know how crazy it is, but it's a decimal. I think it's a non-terminating decimal. That's why it's crazy. Okay, all right. Okay, so you get that. I went ahead and, even if there's an absolute value here, if it's positive, you can go and just multiply it out, right? It's okay, it's equivalent. So you get that. How do you solve that? Fifth root of both sides. So we get absolute value of x is the fifth root of 0.12. If you end up with the absolute value of x equals this, whatever, 0.654383939, then x is plus or minus this, and the x's fall in between, or all x's in that interval. So all x's that we plug in to our approximation would be, that are in this interval, would be within 0.001 of the actual value. And it probably goes even further out because that's the maximum possible. Using the max error. Ready for one more? For this last one, I'm going to show you kind of a cheating method.
Cheating method.
It's my cheating method. It's like it's cheating. I still want you to use the formula tonight for your homework, and I want you to get into that good practice, but I am going to show you for this type of problem that you can cheat.
Yeah.
Yes, if you would like to cheat, here's how. And it's not really cheating, it's just, it's mathematically correct. There's nothing wrong with it. Okay? It just bypasses the formula. All right, so we're going to cheat the system. We're going to find a Taylor polynomial approximation for y equals the cosine of 0.1